Rahmstorf. I'm Professor of Physics of the Oceans at Potsdam University and Head of Earth System Analysis at the Potsdam Institute for Climate Impact Research. The oceans are a crucial component of the climate system. They store 93% of the heat, the additional heat that our planet has absorbed due to the increase in greenhouse gases. The oceans take up about a quarter of the CO2 emissions that we pump into the atmosphere. The oceans delay global warming. They redistribute the heat due to changing in ocean currents, and they have a profound effect on the weather patterns and weather extremes like tropical cyclones. We have to look after the oceans, especially the life in the oceans is very much threatened by global warming and by ocean acidification. Why the ocean is important to everyone. It seems quite obvious. Our home planet Earth really is a water planet with more than 2/3 covered by the oceans. So of course the oceans are very important. But I want to specifically talk about why the oceans are especially important in the unfolding climate crisis. The fact that humans are changing the climate was already noted by the famous German scientist explorer Alexander von Humboldt in the year 1843, when he wrote that humans are changing the climate, quote, by cutting down forests and by releasing large amounts of steam and gas at the centers of industry. By now, of course, the human-caused global warming is extremely well documented. Here we can see in the red line the measured global mean temperature increase over the last more than 100 years since the late 19th century. And it is compared to reconstructions of the global temperature evolution since the last ice age, 20,000 years ago, which we can reconstruct by using ice cores, sediment cores, and other data sources. This is a fruit of decades of paleoclimate research. And we can see the warming from the Ice Age into the Holocene, and then a very gentle cooling trend over the last 5,000 years. Within 100 years, we have bent around this natural cooling trend, and we have more than undone 5,000 years of cooling, which normally would have continued given that these cycles are due to the cycles of the Earth orbit, these so-called Milankovitch cycles. Today we understand the causes very well. We understand, of course, that this warming was predicted before it was observed, and we understand the energy budget of our planet and how it is changed by the increase in greenhouse gases. And so we know, this is a measured fact, how much heat is trapped by these greenhouse gases. And we know that 93% of this additional heat trapped in the Earth system actually ends up in the oceans. That's not because the oceans warm more than the atmosphere. It is because the oceans have a huge heat capacity, so they can store a lot of heat, much more than just the relatively thin air of the atmosphere. You can see the increase in heat stored in the ocean here in these measurements from ships and autonomous drones in the ocean that measure down to a depth of 2,000 meters how much heat is stored there, and it is just going up and up. What this heat storage in the ocean means to us on land is that it delays global warming because a lot of heat disappears in the oceans, and that is the thermal inertia of our planet, and so it takes a while to heat up. Without the heat storage in the oceans, global warming would have progressed already much faster. When we look at the map of global temperature change since the early 20th century, we can see that the whole globe basically has warmed. That's why it's called global warming. with one notable exception, and that is the northern North Atlantic, where we see there has been a cooling in the last 120 years. This is another thing that has been predicted by climate models before it was found, and it is related to changes in the ocean circulation. We're talking about an ocean circulation system in the North Atlantic, which has a major impact on climate, which is shown here in a schematic way in this NASA animation, where a warm surface current flows northward throughout the Atlantic from the South Atlantic across the equator into the Northern Atlantic. There it gives off a lot of heat to the atmosphere. The water thereby gets heavier and sinks down and returns south as a cold, deep current. So the whole thing works basically like a central heating system for the North Atlantic region. And if we look at this not in a schematic way, but in a real climate model, a computer model of the climate system, then it looks like this. The colors are the temperatures, and we see the warm Gulf Stream as a dark red band coming up the United States coast, leaving the coastline at Cape Hatteras, starting to meander there and break up in these eddies. And this is part of that large Atlantic overturning circulation, which transports a huge amount of heat into the Northern Atlantic. And the fact that this region in the North Atlantic is cooling is an indication that this current system has slowed down. In fact, we know more about this because when we look at the temperature changes in this climate model that we just saw in the animation, and we look at how the sea surface temperatures change when you add carbon dioxide to this climate model, to its atmosphere, then a very peculiar pattern in the Northern Atlantic emerges. Now, this diagram shows the difference to the average global warming. So everything that is just warms as much as the average ocean is white, and everything orange has warmed more than average, and everything that's blue has warmed less than average or even cooled. And you see the North Atlantic has a very peculiar pattern with this a large blue patch surrounded by a red patch in the below it in the south, and another red one off Norway. This is a very strange pattern, but in the climate model, of course, we have all the information, so we can really diagnose everything, and we know exactly what causes this pattern, and it is the change in the Atlantic Ocean currents. And my PhD student, Levke Cesar, has spent years compiling all the ocean data, the measurements since the late 19th century, and the observed change pattern looks like this. And we can see a very similar pattern in the Northern Atlantic, very similar to what is predicted by the climate model. And so it's very strong evidence that what we are observing here is also caused by a slowdown of this Atlantic Ocean circulation, also known as the Gulf Stream system. Another aspect how the ocean influences climate is it can freeze over, especially in the polar regions. You can see here the sea ice cover in the North Polar Ocean, what it looks like typically, or has looked like until the early 1980s in the summer. That of course shrinks and grows depending on the seasons, but at the summer minimum it used to look like this. Now it looks more like this. And so we have already lost almost half of the summer sea ice cover on the Arctic Ocean. And I think at least all the people who are younger than, or most of them younger than 60 years or so, they will probably live to see this situation where the Arctic Ocean becomes essentially ice-free in the summer months. In addition, of course, we have the continental ice sheets, the one on Greenland that we're zooming in here now, and this animation is of satellite data showing where the Greenland ice sheet is losing ice through melting. That's all the blue areas. And now we zoom across to the Antarctic. We have a somewhat different picture there, but regionally and in total, the Antarctic ice sheet is also losing mass. And because that is land ice, it adds water to the ocean when it melts, and that raises the global sea level. That is another very logical and totally expected consequence of global warming, that sea levels will rise. For example, you can read that in the 1965 Revell report to the then United States President Lyndon B. Johnson, which warned about the impending global warming due to fossil fuel burning and also the consequences like melting continental ice, sea level rise, all that is already described in that 1965 report. And indeed, by now we know the sea level is rising. It has risen about 20 centimeters since the late 19th century. And for the future, we expect further sea level rise, depending on what we do, on how much further carbon dioxide we will emit. We see, in addition to the observational data for the past, two future scenarios here. The blue scenario is a scenario where we implement the Paris Agreement and we stop global warming well below the 2-degree mark. That means stopping the warming by mid-century. But you can see the sea level continues to rise until the end of the century at a very similar pace. All we can achieve by implementing the Paris Agreement is preventing a further acceleration of the sea level rise. And in the somewhat longer run, if we look at until the year 2300, with the Paris Agreement, we can probably, hopefully, slow down sea level rise eventually enough to keep it within 1 meter by 2300. But in the red scenario with unmitigated emissions, we'd already end up by 2100 with 1 meter, by 2300 with 4 meters of global sea level rise, which would wipe out many coastal cities and small island nations. For example, the Maldives. This image shows, I think it makes immediately clear that there is very little chance to protect the Maldives even from very moderate sea level rise, and indeed the Maldives are already building a new island that will be 2 meters higher, where they plan to resettle much of the population. This, of course, is a very special situation. By far, most of the coastlines and the coastal populations could not adapt like this to rising seas. Sea level rise is a very slow-moving problem because it takes a lot of time to melt the continental ice sheets. It also takes a lot of time to heat up the ocean down to significant depth, which is another factor in rising seas, because when you heat up water, it expands, thermal expansion. And so there are long-term, very long-term scenarios for the future sea level rise that show that even with a warming limited to 2 degrees, in the long run, over thousands of years, we would expect about 25 meters of global sea level rise. This is the kind of thing that we are committing future generations now by what we are doing in the coming few decades. And even in this Paris scenario, in the long run, the rate of sea level rise will reach a peak of 3 meters per century, which is of course much faster than the 20 centimeters that we have seen in the last century. That cover image of National Geographic, by the way, shows the level to which the sea level would rise if we melted all the continental ice. That would mean 65 meters of global sea level rise. That's as much as ice that we still have. Just as a comparison, at the end of the last ice age, the sea level rose by 120 meters with that warming of about 4 degrees from the ice age climate into the Holocene. So this 65 meters of sea level rise would reach the level at the Statue of Liberty that you can see there on that old National Geographic cover. Another influence of the warming oceans on our climate is hurricanes, because hurricanes draw the energy that drives them from the warm upper ocean waters. That's why they are called tropical storms. They exist in the tropics, where the ocean is warm enough to sustain hurricanes. That animation was of Hurricane Florence that hit the United States coast last year. And it has long been predicted by climate scientists that hurricanes will not necessarily get more frequent, but they will get stronger with global warming. And an analysis of satellite data shows that in 8 of these regions where tropical cyclones exist, in six out of these 8, the strongest storm on record has been in the last few years. So that is one indication of the intensity of tropical storms actually increasing, as the laws of physics would suggest. But there's an even more recent study from early 2020. Here we see a beautiful nighttime image of Hurricane Laura, which hit the Gulf Coast of the United States a few weeks ago. And a quite recent study earlier this year in the proceedings of the National Academy of Sciences has shown that from the satellite data since 1979, when you take intensity measurements of the hurricane based on the cloud structure from the satellite, and you look at what proportion of all intensity measurements of hurricanes have a major hurricane strength, so that means the strongest categories, 3, 4, and 5 of hurricanes, then this proportion has increased by about a quarter, from 32% to 40%. That's another confirmation that the expected increase in hurricane intensity, expected from the laws of physics, is indeed happening. Let's have a look at the atmospheric circulation, which is also affected by the oceans. And this is a very recent area of study. It is looking how changes in the atmospheric jet stream, which circles the northern hemisphere in about 10 kilometers height, are occurring. And the leftmost of these globes shows a pretty straight jet stream going around the northern hemisphere. The second one illustrates how normally it has some meanders going north, swinging north and south. And in these are the high and low pressure systems embedded, and they move typically from west to east with a kind of normal progression of pressure systems in the northern mid-latitudes. Now, the third globe from the left shows a very special situation where occasionally the meanders in the jet stream become very large, very regular waves, and the whole pattern starts to stall. It becomes stationary for weeks on end, and this leads to some very strong weather extremes, like, for example, in July 2018. And depending on where in these meanders you are, you can either have a heat wave and fire problems like in the western United States, or simultaneously flooding problems like in the eastern United States. And these resonance events of very strong waves in the jet stream are becoming more frequent, and they can lead to synchronous extreme weather events around the whole northern hemisphere, like in 2018. Now, the ocean is not only affecting the physics of our planet, but also the biology. And I'm just showing one example here, which is the coral reefs. It has also long been predicted by coral reef experts that the coral reefs will be very negatively affected by warming ocean temperatures. And indeed, this just shows in 2015 and 2016 major coral bleaching event due to hot temperatures, which has affected most of the coral reefs on the planet, including the Great Barrier Reef in Australia, the largest reef. And careful studies have shown that the coral bleaching correlates very directly with how warm the oceans got in those regions where it got particularly warm, so-called marine heat waves. We see the most detrimental damage to the corals. It's very sad to lose these fantastic natural systems that also provide flood protection. They provide a lot of biological diversity, a lot of abundance of fisheries that many hundreds of millions of people depend on also for their nutrition. Another aspect is that the ocean affects what we call the biogeochemistry the most important thing is that the ocean takes up about a quarter of the carbon dioxide that we are pumping into the atmosphere simply through gas exchange at the ocean surface. And if this wasn't the case, the CO2 levels in the atmosphere would have risen even faster. The warming would have proceeded even faster. So in a way, it's lucky that the ocean takes up a quarter of our CO2 burden, but it has a downside, and that is CO2 dissolved in ocean water leads to acidification, carbonic acid. And this has a negative impact on marine life, not only on the coral reefs, which are also affected by that and will increasingly so in the future, but there are many species of microplankton that form calcium carbonate shells, like these beautiful ones shown here. And on the left you see what a normal microplankton shell looks like, and on the right you can see how it gets corroded by seawater that is too acidic. And if we continue on the current path of CO2 emissions, by the second half of this century we will get ocean regions which are so acidic that the normal seashells that you know from the beach will start to dissolve in the ocean water. This is a pure and very simple, undisputed chemical effect of the increasing CO2 levels that we put in the atmosphere, and that some of which ends up in the oceans. So the patient Earth is in a not very good shape, but the doctors are there, and they have agreed on a therapy. It's the heads of all nations agreed in the Paris Agreement of 2015 to stop warming well below the 2-degree level. We've already reached about 1.2 degrees centigrade, and pursue efforts to limit the warming to 1.5 degrees. And to finish off, I just want to mention the main thing that this means for us. It basically means that we can only emit a limited amount of carbon dioxide. That is our CO2 budget that we have left for humanity, and it's less than 800 billion tons. We are emitting more than 40 billion tons a year now, and we have about 20 times the amount of carbon locked in the fossil fuel resources. So what this means is 95% of the known fossil fuel resources are unburnable carbon. We can't use it. And for investors, that means stranded assets if you invest in fossil fuel companies. So let me come to the conclusion. The ocean affects us all, and I have shown that the ocean is warming, the seas are rising as a result. There are changes in the ocean currents that we are starting to observe now that have long been predicted. The coral reefs are increasingly in their death throes, and other marine life is also negatively affected. I couldn't go into this in more detail in this talk. We see stronger hurricanes, more weather extremes. I could have mentioned more extreme rainfall coming with the stronger evaporation from the oceans. And I've mentioned the uptake of carbon dioxide by the oceans, which leads to ocean acidification and threatens marine life. So this problem is getting more and more urgent. It took 50 years of discussions from the first official government report, the Revell report in 1965, until there was finally agreement among all nations in 2015 in the Paris Agreement that we must stop this problem. And by now time is running out, so every year counts. Thank you very much for listening, and if you want to read more, there are these books that I have co-authored, and you can read my blog or follow me on social media. Thank you very much for your attention.